Hey guys, welcome back to another video. Today we are going to be writing a matrix struct from scratch in Mojo. I'm excited and I hope you guys are excited as well. A lot is going to be covered in this video, so we're going to be talking about how to write structs in Mojo, which is basically a class in Python. And we're also going to be talking about how to do some memory allocation stuff and how to use pointers using Mojo. And we're also going to cover dunder methods, which stands for double under methods. You've probably seen them before. It's the methods with double underscores. And we're also going to go over some Mojo keywords that are used for methods. And finally, you can learn a bit more about matrix operations. Okay, so let's start with some coding. So I'm in VS Code right now, and I've created a folder called matrix. And in here, I have a main file and a matrix file. In the matrix file, we're going to be writing our matrix struct from scratch. And you guys told me to enlarge the font size, so I did. I hope this is larger for you guys. Let me know if you guys want it even larger. Okay, so let's start writing our matrix struct. So in order to write a struct in Mojo, you first write struct and then you give it the name. So we're gonna call it matrix. And let's just say we can write a doc string here. Let's say simple 2D matrix that uses float32. For simplicity, we're just going to be working with float32. You could try other ones if you want. Okay, and let's start by defining some few instance variables that we might need, like var height, right? The height of our matrix, and by that logic, also the width of our matrix, right? So these are our matrix dimensions. And let's also define a variable called total items, the total number of items in our matrix, which is just width times height, right? Okay. Now, for any class, you have to write an init function to initiate it. So let's write that, init. This is just exactly like Python, but in here, for self, we have to use the in-out keyword. So basically, this stands for inside and outside. So if you modify self inside this method, it will also be modified outside this method, which is exactly what we want. Okay, and let's just also define a default value, which is float32. And what this is that we want to initiate our matrix with a single scalar at first. So let's just say our matrix could be like 2, 2, 2, 2. So this is what the default value here is 2. So we initialize our matrix with 2. It's just for ease of use, I guess. And we also need the height, which is int, and width, which is int. Okay. And since we're initializing a method, we don't have to return anything, so let's just return none. Okay, and then it's just self.height equal height. But keep in mind that what if they don't pass in a height for us, right? Then we could just assume that the height is 1. So we could check if height is greater than 0, else 1, right? So if they don't pass us a height in the initiation of an object, then we just assume the height is 1. Okay? And same logic for width. Self.width equal width if width greater than 0, else 1, right? So if the width is greater than 0, we just set self.width to width. Otherwise, set self.width to 1. Okay? And self.total items, this is just equal to width times height, like we said previously. Okay. Now, if we're trying to store elements on our matrix, how can we do that, right? We haven't really discovered how we can store elements. Well, to do that, we use pointers. And let's define a variable for that. let's call data, and it's going to be a pointer float32. So the purpose of this data variable is to define a pointer that points to a memory location storing floating point numbers of type float32. And this is essentially the address of a block of memory that will store the elements in the matrix. So let's understand memory allocation and pointers from scratch. You can think of memory as an office files cabinet here. You can store items into these individual drawers in this cabinet. And you can kind of think of variables as these individual drawers. Each drawer can store something, and it likely has a label so you know what the drawer stores. For example, this label could be pencil, so you know that inside this drawer is going to be storing pencil, right? So the label of the drawer is the variable name, and the content inside the drawer is the value of the variable. And this entire big cabinet is where these drawers are stored together, and that is the memory. Okay. So what are pointers? You can think of each individual drawer as variables, and they each have an address, right? For example, the address of this drawer could be FE0FFEEB. That's just the address, like the address of your house, for example, right? And a pointer essentially points to the address of the drawer, right? It points to where this drawer is. And this is different from variables. Variables have names, but the name is not the same thing as the address of the variable. Okay, so that's what pointers are. Now, let's go back to writing our code with this in mind. So we're back in VS Code, and now with that in mind, let's figure out how we can allocate our memories. Okay, so let's say self.data equal pointer, and this is going to be float32, right? Like we defined up there, and we gotta do .alloc, which stands for allocate, and then self.total. So what does this do? It's basically asking for a certain number of empty drawers to be reserved for us in the cabinet. So let's say our matrix has 4 elements, then we're reserving for 4 drawers in the cabinet. In this case, this is the memory. So we're reserving for 4 spaces in our memory. Okay, so we're back in VS Code, and now let's see how we can allocate and store individual default value into these drawers, you could say. So let's loop through it. In range self.total items. So we're just gonna loop from 0 to total items, and we can just do self.data.store I and default value. So we can use store to store the specified value, in this case default value, to the location the pointer object points to with the given offset, which is I in this case. So you can think of it as like a 1D array, and then we're flattening our matrix to be stored inside that 1D array. Okay, but in this case it's memory. Okay, cool. So that's our init function. This will make more sense once we define how we can retrieve a specified element in our matrix. And why don't we do that now? Okay, so we're gonna write a dunder method here called getItem. And the name for the dunder method, you have to look into the Mojo documentation for the specifics. And in order to define a dunder method for retrieving a specific element in our matrix, is going to be called getItem. Okay, and in this case we're going to use the borrow keyword for self, because we aren't modifying self, right? We're just retrieving a specific element in the matrix, so we could use the borrow keyword. And the borrow keyword essentially ensures that the self is passed as an immutable reference, meaning we cannot modify self in this function, and we don't need to, right? Okay, cool. And we also need the row, right? Where is this located in terms of row? And by that logic, we also need column, because we need to access the where this element is located in our matrix. Okay, and now this is going to return float 32, right? Because we're storing every element as float 32 in our matrix. And then we can do, since we're storing it, you can think of it as a 1D array, then we can't just access it like a 2D array. So we have to do something else. So let's say log, let's define a variable called log, and this is equal to row times self.width plus column. So essentially what we did here is that we pretty much flatten out where this location would be if it's in a 1D array instead of 2D array. So we just flatten it out, right? Okay, cool. And by the way, let here means that this is constant. If you use JavaScript, this might seem non-intuitive, but let here actually means that log is a constant inside this method. Okay, and if we also have to check if they're accessing something that's outside of the matrix, right? They're accessing something that's not even inside the bounds of the matrix. If that's the case, which means that log has to be greater than the total items that we allocated, right? If that's the case, then let's just tell them that they're accessing, warning, you are accessing an index out of bounds. Let's just tell them that, okay? And since we're still returning a float 32, let's just return 0, return self.data. Let's just return the first element, right? So this load here loads the value the pointer object points to with a given offset. And since we're providing 0, it's just returning the 0th index. Okay. And let's just return self.data.load log otherwise, right? So basically, if we return here, we wouldn't even be able to run this code because return ends the rest of the statement and prevents them from running. So if this if statement is false, then we will run this. If this if statement is true, we will run this. Okay, so this is how it works. Get item. All right, cool. Okay, so we figure out how we can retrieve an item. Now let's see how we can define a function to set a specified location to a value, right? We got get item, let's do set item. Set item. And again, you can look into the Mojo documentation for where I'm getting these names for the Dunder methods, okay? And in this case, we're going to use in-out self, right? Because we're setting an item in our matrix. We're modifying our matrix, so we can't use borrowed like before. Okay, so again, we need the row, which is n, and column, which is n, and the item, which is float 32, right? Because we're setting an item this time, we have to set it to a specified value. And we're returning nothing in this case because we're setting the value. Okay. And again, we can just copy this code pretty much. Let's read. And since we're returning nothing, we just click return, and this will prevent the rest of the code from running. And then we can do self.data.store, and at this location we're storing item. Okay, so let's see how this works. So we provide the offset, which is log, and the item, which is value, okay? The value to store. So that's what we're doing with this. And boom, that's it. That's how we can store an item in our matrix. So I hope that is clear. Now let's do something that you probably haven't seen if you only used Python before. We're going to define a delete function that allows us to delete this current matrix object we have initialized. And let's see what that looks like. So again, it's fn for function, and in this case the Dunder method is called delete and owned self. So what does the own keyword mean? The own keyword here is used to indicate that the function takes full ownership of the object it's called on. Okay, so that's why we're using the own keyword. And to free up this memory, or in other words, delete this, we can just do .free. Right, so going back to our cabinet analogy, calling .free here basically tells the cabinet that, oh, we're no longer using these set of drawers, you can have it back, right? So that's essentially what this is doing. And those drawers get freed up and can be used again, right? So yeah, this is what delete does. And this basically deallocates the memory used by the matrix when it is deleted. And this way, the matrix doesn't take up memory when we don't want to use it anymore, right? Okay, cool. Now, let's also define a simple length function just to get the length of our matrix, which is just the total number of elements. And in this case, we can do borrowed self because we're just retrieving something. We're not modifying the matrix. And we're returning an int, right? And this is just self.total.items. Really simple. Okay, cool. And another functionality that might be useful for our matrix is a way for us to set a new matrix to the values of another matrix. So basically initialize a new matrix by copying the values from another matrix. So how can we do that? Let's see it. So in this case, it's called copy init. And we're gonna have in out self and other, which is of data type self. So we're initializing our matrix, so the self matrix for the first time by copying elements from the other matrix. Okay, so that's why we use in out here, but it's basically init, but we're copying it from the other matrix in this case. Okay, cool. And we can do self.height equal other.height, self.width equal other.width. We're copying the dimensions of the other matrix, and then self.total items equal other.total items. And then here we have to do self.data equal pointer, and again it's float 32, and then here we have to allocate self.total items again because we have to initialize a new set of drawers to use, right? We can't just use the same drawers that the other matrix is using since we're copying them, right? Okay, and then so how do we copy it? We can do memcpy. This is a function we could use, and it's float 32 and it takes in self.data, other.data, and then we can do self.total items. Let's see this documentation. So it takes in the destination, which is self.data in our case, and this is going to be a pointer, right? And then we have the src, which is where we're getting this data from. Well, it's from other.data, right? And again, it's a pointer. And the count, so the count is the number of elements to copy. Well, that's just self.total items, right? We can also write other.total items, and that will work just fine. Okay, cool. And this documentation is very well written. This says copies a memory area. Okay. So we could use an analogy to understand this intuitively. So imagine you have a bookshelf full of books, and you want to create an exact duplicate of the bookshelf. Well, first you have to measure the dimensions of the original bookshelf and build a new one of the same size. Then you take each book from the original bookshelf and place a copy of it in the exact same position on the new bookshelf. Now you have two separate bookshelves with the exact same books. Changing one won't affect the other, and this is essentially what the copy init function does, but for matrices in our case. Okay, cool. Let's see what now. Okay, now we probably want to check if two matrices are equal to each other, right? well, to do that, we could write a comparison operator to determine that. So in this case, it's called EQ. It stands for equal, and in this case, we just pass in borrowed self because we're not modifying self. And let's do RHS. And RHS stands for right hand side. So this is the matrix on the right hand side. So if we do matrix 1 equal matrix 2, RHS is matrix 2. Matrix 1 is self, right? So what EQ allows us to do, we're returning bool, and this checks if this is true, right? If they are equal, then we return true. Okay, that's basically what we're doing. So how can we check that? Well, we can do that with a simple for loop. For I in range, self.height, and for j in range, self.width. Well, right, we're looping through every row and then each individual column. That's what we're doing here. Let self-val, which is float32. Actually, let's let Mojo infer the type on its own, and we can do self-ij, right? This is really cool, right? We define how we can get item up here, right? Given a row and a column, and we're doing that. We're using it right now by passing it an I and j, row and column. We're accessing elements in the matrix, which is really cool, right? Okay, and let's also do it for RHS val equal RHS I and j. Cool. And if they're not equal, right, then we should return false. If self val, oh, actually, in this case, we haven't defined how we can check if they're not equal. So we can't use that yet, right? We can just do not equal RHS val because we haven't defined this yet. We're going to define that next. So we could just do if it's less than RHS val or self val is greater than RHS val, right? If this is true, then we return false, right? We don't need to define how we can compare to float32, right? That's implemented for us, so we can just use this instead, right? Okay, cool, and we return true at the end. So if this returns false, we won't even run this line, okay? Cool. And if this statement is never true, then we will just run this line. Cool. Now we can implement this, right? So it's gonna be called NE, which stands for not equal. And again, it's gonna be borrowed self, RHS, matrix, and it's gonna return a bool. And this is gonna be really simple since we already determined how we can check if they are equal. So we can just do return not self equal RHS, right? So we can use the equal now. And this checks if they're equal, and not basically means the opposite. So if they are equal, then we return false, because think about it. This operator, so matrix 1, matrix 2, this operator returns true if they are not equal. So the opposite of checking if they are equal, right? Okay, so cool, we defined the not equal. Now let's define some operators, right? Our matrix needs to be able to add and subtract and multiply and divide. Let's define those arithmetic operators. Starting with add. So add, borrowed self. We're returning a new matrix, so we can just use borrowed self here. And also right hand side matrix, and it's going to return a matrix. So essentially we're trying to do plus matrix RHS, right? Let's just do matrix 1 plus matrix 2. That's we're trying to define this add functionality here. So if self.width is not equal to RHS.width, or we're gonna check if their dimensions are equal or not, because you can only perform matrix operations if their dimensions are equal, right? So if this is the case, let's just say error cannot at matrices if the width or height of one is not equal to the other. Right, just a simple error statement letting them know. And we can just return matrix float 32 0.0 self.height self.width. Right, if this is the case, let's just return a 0 matrix. And notice here we're using the init function. Isn't that cool? So we're initializing a new matrix, and it's going to take 0 as the default value, and then self.height and self.width. So it's just going to be a 0 matrix, like 0 0 0, for example, right? Cool. And otherwise, what should we do? Well, let's define a new matrix. We're going to use the var keyword here, which means that this is mutable. We can modify it, unlike the like keyword. So new matrix. Let's just let it infer on its own, shall we? Okay, so matrix float, again, float 32 0.0 self.height and then self.width, right? Cool. We're defining a new matrix. We're going to initialize it with 0 at first, and then for I in range self.height, for j in range self.width. New matrix I j equals self I j plus RHS I j. Cool. Again, we're using get item here, accessing a specific location and the value there, and we're gonna set it, set new matrix at this position to the sum of these corresponding rows and columns of self and RHS matrix. So that's how matrix addition works. And at the end here, we can just return new matrix. Cool. Awesome. And if you notice here, we're actually using set item, right? Cool. All right. Now let's also define subtract, and it's gonna be really similar. So I'm just gonna copy and paste this to save you guys some time. Subtract not equal, cannot subtract, right? New matrix, everything stays the same except here we're subtracting. All right, cool. Now addition and subtraction are pretty simple, but multiplication gets harder. Let's go through this implementation slowly. So it's gonna be called mo and borrowed self because we're returning new matrix, and then oh my god. Okay, it's gonna return new matrix. And for matrix multiplication, you actually cannot multiply them if the width of the first matrix is not equal to the height of the second matrix. So if self.width not equals self RHS.height, then we print error, cannot multiply matrices if the width is not equal to the height of the other. Alright, cool. Now we can just return a 0 matrix again, like that. Okay, cool. Now let's define a new matrix. Var new matrix equal matrix. Let's just copy this. Alright, cool. New 0 matrix, and we're gonna loop through each row of the self matrix, and then for that row we're gonna loop through each column in that row, and then we're gonna loop through each column of the RHS matrix, and we're gonna loop through each row in that column of the RHS matrix, and we're gonna multiply them together. So how can we do that? Well, we can do for I in range self.height, and then so we're looping through each row in this case, and then for j in range RHS.width, we're looping through every column of the RHS matrix, and then we're going to do for k in range self.width. And this basically loops through each element in the current row of self and then the column of the RHS. We can also do other dot height here, since self.width must be equal to RHS the height if we reach thus far. Okay, so how can we set the values then? Well, new matrix ij. Notice that we plus equal self I. Okay, we're not just setting it equal to this because this is the dot product, right? So we have to do plus equal. Okay, cool. And then we just return new matrix. So if you don't understand this part, it's confusing to you, I highly suggest getting a pencil and paper to write it by hand and seeing how it works on paper. Okay, and this function basically allows us to do matrix 1 times matrix 2. Okay, and yeah, use a pencil and paper and get a sense of how this works. Okay, cool. Now let's also define division. It's going to be called true div, and then borrowed self RHS matrix, and it's going to return a new matrix. Okay, and honestly, it's going to be really similar to subtraction and addition. It's going to be element-wise division, so we can just do this, cannot divide, and then down here we just divide. Okay, cool. That's it. Really simple. Now we also have to consider the case if we want to add, subtract, multiply, or divide our matrix by a single scalar value, then we can't use these functions. So we have to define new ones to consider those factors. Fn, and this is called overloading, by the way. So based on what they pass in for the operations, we can account for that. So again, it's going to be borrowed self RHS. This time it's going to be a float 32. Okay, and we're returning a new matrix after we add RHS to every single element of self. Okay, let's just copy this. I can't be bothered. Okay, plus RHS, boom, simple. And let's just do the same for subtraction. Float 32, okay, cool, minus RHS. Multiplication is going to be really simple this time because we're multiplying it by a scalar. So we can just copy again. Mo times RHS. Okay, and then division, true div, divide. Alright, cool. Boom, easy. Now, let's also consider the case where if we want to apply another function to our matrix, like for example, we define a function and we want to apply it to every single element of our matrix. How can we do that? Well, we can just define a normal method, not a dunder method, just a standard method called apply function. Okay, and this is gonna take in a function. Let's call the function and then float 32. The function is gonna take in float 32 because each element in our matrix is float 32, and it's also gonna return float 32. So it's gonna apply this function element-wise for our matrix. And here we're gonna use borrowed self because we're returning a new matrix. And then we could just copy this code mostly. But in here, we have to change this line equals func. We're applying this function to this position of our matrix. Alright, cool. And that should work as expected. Now let's save this file and write some test cases on our main.mojo. So we can do from matrix import matrix. So we're importing the matrix struct from our matrix.mojo file. and then fa main. This is the starting point for our test. So we can define a new test matrix equals matrix float 32. Let's say it's 3 and then 2 by 2. Oh shoot, guys, I forgot. We also have to write a print statement so we can print each element of our matrix. To save you guys some time, I'm just gonna copy and paste it. And I'm gonna explain. So this is the print all function we're gonna use. So it first prints a bracket, and then we're gonna loop through every element and then embed another bracket in here. And then print new line basically means that it won't start a new line after this print statement. And then we're gonna print the individual elements in here, and as long as it's not the last element in this individual row, then we add a comma at the end, okay? And then we close it off at the end. So let's see how this will work. Let me save this file. So we can do test matrix.printall. Let's run this in our terminal. So we can do mojo main.mojo. Oh, sorry guys, I have to go into our matrix folder. Let me run that again. Okay, cool. So, we're able to print out our matrix, which is of type float 32, and each element is a 3. That's our default value, and it's 2 by 2. Okay. Ignore the warning for now because we are going to modify our test matrix in a bit. Okay, cool. Now let's define a second test matrix equal matrix float 32. Let's give it 9 and then 2 by 3. Second dot print. Let's try that. Ignore the warnings and boom, 9. Exactly. Okay, cool. Now let's do second test matrix equal test matrix. Second. So let's see if our copy init function works. Okay, cool. See, now second matrix is now equal to 3.0. Alright, cool. Now let's check if our equal operator works. Test matrix equal second test matrix. And let's also check if our not equal operator works. And true and false. Boom, exactly. Okay, cool. Now let's test everything. Let third test matrix equal. Okay, let's try if that works. Boom, 6, exactly. Okay. To save you guys some time, I'm just gonna copy some code to test these for us. Okay. Alright, so these are the code that's gonna help us test these files. And okay, let me make the terminal bigger. Oh, I forgot to save the file. Okay. Boom. Okay, so basically what we have done is that let's go one by one here. The fourth test case subtracts, so 3 minus 3 is 0, that's correct. The fifth test case, we multiply them together. So 18 that is also correct because this is matrix multiplication. And then divide, 3 divided by 0, 3 divided by 3 is 1, so this is also correct. And then we add them together. This is by a scalar. We're adding 3 to 1, so 4, this is correct. And then subtract, we get 2, which is correct. 3, we're multiplying by 1, and 3 divided by 1. Okay, cool. So everything works as expected. And yeah, that's it for this very long video. If you guys have any questions, please leave them down in the comment section below. I will try to respond as soon as possible. And if you have any suggestions for future videos, please let me know as well. This video took longer than expected. I promise future videos wouldn't be as long. So yeah, thank you guys for watching and see you next time.